Okay, 2005 Form B, question number 3 says the figure above shows 2 point charges, each of a charge negative 2q, fixed on the y-axis at plus a and minus a respectively. A third charge of negative q is placed at 2a on the horizontal axis. Express all algebraic answers in terms of q, a, and fundamental constants. And once again, don't forget that k is a fundamental constant. So it says derive an expression for the magnitude of the net force on the charge minus q due to the other two charges and state its direction. Well, first thing you need to remember that force is k q1 q2 over the distance between the two q's squared. So the first part is fairly simple. I know the force, let's just worry about the force between these two right now. I know that it's k, and then I've got 2q times q over the distance between them squared. Well, this is a right triangle of a and 2a, which means the distance between them is just the square root of a squared plus 2a squared, all squared. Well, I'm actually going to simplify that a little bit. So this is going to end up being k times, let's see here, 2kq squared all over, and this is going to end up being 5a squared, because this reduces down to the square root of 5a squared, because the square applies to both the 2 and the a, so that's a squared plus 4a squared. And then when you take the square of that, you end up with 5a on the bottom, 5a squared on the bottom. So the next thing you need to realize, so this is the force of one of those two q's on the other q. We have to double it since there are two of them. So since we have to double it, this now becomes 4kq squared over, and that 5a squared can stay right there because they're both the same distance. And the very last thing you have to do is state its direction. Well, I know that this charge right here is going to push this way, and I know that this charge right here is going to push this way. So that means my y component here and here cancel out. Okay? But if you look, my x components will add up, one plus the other one. So if I can find the x component of one, I can find the x component of the other. And once again, since I've doubled it, it'll be fine. So what I'm going to do is I know I have a triangle here, a right triangle, and I'm looking for the angle, because that right triangle will match this right triangle, looking for the angle. So in order to find the right triangle, the theta here, I just need to take, let's see here, I know this and I know this. So let's do tangent. Tangent, actually, you know what, since we're doing x components, we need cosine of theta. Cosine is opposite, which is a, over hypotenuse, which we found to be this right here. So 5 square root 5a squared. And actually, it's only going to be 5a because I squared it here last time in the force equation, but I don't want to square it now, so it just stays as 5a, the square root of 5a. So now, adjacent is 2a. Sorry, I'm just forgetting all kinds of stuff. So it's 2a over square root of 5a is my cosine. Well, down here, this is cosine theta, which I can't have in here, but I can replace that with what it's equal to. So 4kq squared over 5a squared times, and if you simplify this down, you end up with 2 over the square root of 5. So finishing this off, we end up with 8kq squared all over 5 root 5a squared. And that is magnitude and direction. Now, I know finding the force between two particles is a real pain in the butt a lot of times, but the good news is after you finish that part, the rest of it comes fairly easy. So this one, part B, says derive an expression for the magnitude of the net electric field at the origin due to all three charges and state its direction. Well, electric field is F over Q, and it is also KQ over R squared. Well, at the origin, so if we look at this, the electric field due to these two, this one and this one, is going to cancel out. So the only one we really have to worry about is the electric field due to this one. Well, the K can stay, the Q becomes capital Q, and the distance between them is just 2a squared, which is 4a squared. Okay, so once again, the electric field at the origin, right here, cancels out because these are the same, therefore they cancel each other out. So that one goes pretty quick. Letter C says, derive an expression for the electric potential at the origin due to all three charges. Well, electric potential doesn't cancel out unless you do it mathematically. So all we have to do is just add up each one of them. And each one of these is just V1 plus V2 plus V3, not forgetting your negative signs, which is just KQ over R plus KQ over R plus KQ over R. So we'll start with the two outside ones, these two up here. So this will be negative 2KQ, and the distance between them is just A, plus minus 2KQ over the distance between them, which is just A, plus, and now the third charge is just Q, and the distance between that one is 2A. Okay, and now it's just a little bit of old algebra, you know. You got to find your common denominator, and you have to go from there. So in order to turn this into a 2A, I got to multiply both sides by 2, so this now becomes a 4. This becomes a 4, and what you're left on is negative 4 minus negative 4, which is negative 8. And it just actually occurred to me, I forgot the negative sign on this right here. This is also a negative. Negative 4 minus 4, which is negative 8. So negative 4 minus negative 4 minus 1 is negative 9 KQ. And then that all goes under 2A. Now just remember that there is no direction for electric potential. It is just a scalar quantity. All right, part D says sketch a graph of the force F on the negative Q charge caused by the other two charges as it is moved along the x-axis from a large positive to a large negative position. Let the force be positive when it acts to the right and negative when it acts to the left. Okay, so what they're saying is we're going to take this charge right here, and we're going to move it from a very large positive position, and we're going to scoot it along the axis to a very large negative position. And they just want to know the force. Well, just think about it. As this negative Q gets closer to these two charges, the force should increase. And remember, it's exponential. It's over r squared. Force is over r squared. But once it hits the center, these two forces are actually going to cancel out. So this thing is going to take a dive right towards the origin. And now that it gets on the other side, it's actually going to be forced away exponentially. So that's what your graph should look like. So the force increases, and then as it gets like in between them, it goes to 0, and then it spikes up again on the other side, and then degrades exponentially as it goes on. All right, that was the end of that problem.